Hi there, welcome back to the channel. In this video, we're going to be talking about alkynes. Before we start, I'd like to apologize for releasing it quite late. It's just that some of my physical students requested for physics videos more than organic chemistry. That was why I stopped for a while. All right, so eventually we're going to be going into alkynes, and hopefully by the end of this next week, I should cover up all that we need to know. So in this video, we'll cover alkynes and hopefully benzene in the next. So now, what are alkynes? So we are basically going to go from the basics to and build it up, okay, just the way we did in alkanes, alkenes. Then we'll talk about the reactions. Now, also keep in mind that I am going to show you a little bit of mechanism here, right? But for you to understand mechanism too, make sure you see my video on 30 things that you need to know in organic chemistry. So when you see that video, it's going to launch you into, it's going to give you a solid foundation for your organic chemistry course. Now let us go into alkynes already. Now what are alkynes? So primarily alkynes are a group of unsaturated hydrocarbons. So they are unsaturated hydrocarbons. Keep in mind that they are hydrocarbons. So, and that means that, of course, they are organic compounds that are not hydrocarbons, okay? So primarily hydrocarbons are alkanes, alkenes, alkynes, and arenes, okay? So, but these ones are alkynes, so they are also hydrocarbons. But this word is very important, unsaturation. I'm going to discuss it in detail later. So I said they are unsaturated hydrocarbons with carbon-to-carbon triple bond. Okay, so that's going to look like this. Let me shorten it. So that's going to look like this, carbon-to-carbon triple bond. That's C triple bond C. Okay, so and this marks their functional group. This is their functional group. Remember, functional group is the atom or group of atoms in a particular moiety or compound, organic compound, that determines the chemical property, right? And of course, it serves as the reaction center. So most of the reactions that happen with any particular organic compound happens at the functional group, or happens to the functional group. You understand? Because it basically transforms it usually. Now, my point is that they have carbon-to-carbon triple bond. And in that case, we said that this guy is called their functional group, right? So they usually have the general molecular formula CnH2n minus 2. H2n minus 2. We're going to review this in detail soon. Now, another thing is that these carbons that bear the triple bond are sp hybridized carbon. sp hybridized carbon. All right. So make sure to see that video on Introduction to Organic Chemistry, and as well 30 things you need to know in organic chemistry. I have discussed hybridization in great detail. So now, sp hybridized carbon. Okay, these two carbons, every other carbon might be sp2 or sp3, depending on whether it is single bonds all through or double bond are also attached. But as far as these two are concerned, this is sp hybridized. Okay, so which means that they possess 50% S character, 50% P character. That is the orbitals that contain this C triple bond C. Now, since sp hybridized, the carbons are sp hybridized, then their molecular geometry, is going to be linear. Okay, it's going to be linear, and that means that the bond angle is going to be what? is going to be what? 180 degrees. I'll go on a straight line. Is that clear? So that is why, you see, this bond angle is very important when you draw the structure of alkyne. Now, there is no kink or bend. No kinks. No kinks. Kinks means bends, okay? So, for example, in alkene rather, make sure to also see the video on alkene. When you see a double bond, you're likely to see a bend at a particular angle, which is actually 120 degrees. But with alkynes, there's no kinks, no bends, all right? I mean, except if you are looking at substituents attached. But on the parent chain is always straight, which is contrary to what we see in alkenes. All right. So these are the general properties that describe or that define an alkyne. An alkyne is unsaturated hydrocarbon that has carbon-to-carbon triple bond, with that being the functional group. Okay, so I said that is the functional group, and it has a general molecular formula. This now sp hybridized carbon, geometry being linear, and the bond angle is 180 degrees. Now, they contain, okay, now I'm not done with the definition. They also contain, since the triple bond is made up of 2 pi bonds, made up of 2 pi bonds, 2 pi and 1 sigma bond. Is that okay? 2 pi's and 1 sigma. Okay? Now, so this is what defines them. Now, let us take this key term on saturation. You should keep in mind. Now, I am trying to make sure that you understand all these things for exam purposes. You see, unsaturation is a very important term. We use unsaturation for both alkenes and alkynes. Okay? Why? Because they are the ones that possess multiple bonds. So once there is multiple bond, in fact, unsaturation refers to what? Multiple bonding. Once it is more than one bond between two carbons, that is unsaturation. So, and with alkenes, of course, we see double bond. With alkynes, we see triple bond. So unsaturation is very important. Take note that it refers to both of them, not just alkynes or not just alkenes, and never alkane. Okay, alkanes are saturated. Alkanes are saturated. So unsaturation is the reason why alkenes and alkynes are able to undergo addition. So now think of it as, I've told you this before, that you should think of unsaturation as if you eat and you are in sachet, and you say, in my place, say I've not belly full. So that belly full is like I've not eaten enough. Okay, so in sachet there means you need to take more, right? So you need to add more food to your stomach. So this addition reaction, this unsaturation means they need to add more to them. So, and that the center for that addition reaction is that triple bond. The triple bond is being broken severally so that molecules or atoms can be added onto the bond. The pi electrons can be used to form bond with other molecules. So that is addition reaction for you, okay? And so the reaction that defines this guy is addition reaction, and for all other organic compounds, combustion reaction. So these guys undergo addition and combustion reaction as well, okay? We're also going to see other reactions when we begin chemical reactions with alkynes. Now, their general formula, very important. Now, this general formula is what we're going to use to form their homologous series. Now, their general molecular formula is CnH2n minus 2. Now, this tells you a very important thing about them. Now, let's compare alkenes and alkynes. Alkenes and alkynes. Now, you know that this one, their general formula is CnH2n plus 2, this one CnH2n, and this one's CnH2n minus 2. Now watch. If I decide to pick any number, let's say I pick 6, for example, or 7, let me pick 7 for my n. Now, if I pick 7, this will become C7H2 into bracket 7 plus 2. You already know how to do this. That becomes C7H14 plus 2, 16. Now, I'm trying to build something up. Watch. I want you to see the ratio of carbon to hydrogen in each of these atoms. So this guy is going to be C7H14 if you solve. This one becomes C7H12. Now, what do you notice? You're going to notice that this guy contains more carbon to hydrogen ratio than the rest of them. Now, you might think that what does that mean? What that means is that gram for gram, there's more, not gram for gram now, that is in percentage of abundance, there is more carbon to hydrogen than there is more carbon to hydrogen in alkene. There's more carbon to hydrogen occurrence in proportion, yes. In proportion, carbon to hydrogen, carbon is abundant relative to hydrogen in alkynes than is available in alkenes and of course in alkyne. In alkene, for every 7 carbons, we have 16 hydrogen. In alkenes, for every 7 carbons, we have 14 hydrogens. And in alkynes, for every 7 carbons, we have only 12. So it means that when you compare the ratio of the abundance of carbon to hydrogen is more in alkynes than alkenes and alkenes. And that really impacts their chemical properties, okay, physical properties rather. I'm going to tell you how that impacts their physical property and chemical properties. All right, so now you know that, right? Okay, so that's what I wanted to talk about here. So let's use it to build their homologous series now. So the homologous series is going to begin with a molecule that must have carbon-to-carbon triple bond. So if something must have carbon-to-carbon triple bond, then this can only be the simplest form. Does that make sense? So this is the only simplest form it can have. It can never have a molecule that will have only one carbon, because the essential functional group is C triple bond C. Is that clear? So we call 2 carbons. What do we call it? 2 carbons. We call it F, right? Okay. Then their family name is going to end with "ine." Ine, right? So F-ine. Is that clear? Ethine. So we have 3 carbons. That's going to be what? Propine. I'm going to draw those for you, their structures. Now then we have 4 carbons. So what's that going to be? We're going to have boot, you remember? Then ine for the family name. Then 5 carbons. That's going to be pent. Then ine. Exactly. So I'll stop here. You can, build it up to decyne. Exactly. The 10 carbons. So this guy is going to have molecular formula C2H2, and the structural formula is going to look like that: 1, 2, 3, CH. Now, the skeletal formula is what students sometimes have problems with. Okay, so watch what I'm going to draw. So this is going to look like this. We usually draw only the bonds. So here, when I draw this, this is actually ethine. So this is ethine. Now, it might confuse students, and I tell them, okay, this is what you should do. Put in that middle line, dots to represent the fact that there is a carbon here and there is a carbon here. So those dots represent the carbon. Now about propine, if you were to draw propine molecularly will look like this. C3, 3 C's, and H, when you double H and subtract 2, that will be H, 4. Makes sense? 2 times 3, 6, minus 2, 4. Then, of course, structurally, that's going to look like this. CH3 on this side, CH3, then C triple bond CH. So this is what it's going to look like. This is actually not full structural formula. This is condensed formula, okay? This condensed formula. So what that means is that if I wanted to stretch it out, I'm going to have C1, 2, 3, C, then triple bond, C, then H. Exactly. So, but I'm showing just the condensed formula. Now, let's draw the structure. Now, stick with me now. The skeleton is going to look like this. It's going to look like this. Then you might now think that why did I not kink? For example, if you wanted to draw propene, if it was propene, don't worry, just stick till the end of this video. You're going to learn many things if you don't even know how to draw skeleton before. If you wanted to draw propene, you know propene is going to be C3H6, right? So the way you would draw it is 1, 2, 1, 2, 3, right? Then you now put a double bond somewhere, whether in the beginning here or at the end here. Now the reason why you could kink here, you could bend this molecule here, is because this guy in geometry actually allows for a bend here. So there's going to be a bend here around the double bond. That's the truth. Okay? So that even at the end, the hydrogens attached are going to look like this. Do you understand now? So that's how you can bend here. But here, it is a linear molecule. Remember, it has a linear geometry. So because of that, from here to here, it has to be 180 degrees. So we draw a straight line. So that to not confuse you, like I said, put a dot here to represent the last carbon, and here the middle carbon, and another carbon here, which is, so there are two terminal carbons and a carbon here. Exactly. So that is propane. Then butane is going to look C4H, double 4, that's 6 now. Then, of course, you have CH3, CH2, C triple bond, CH. Okay? So you have 1, 2, 3, 4. So by the time you write this, you want to draw the skeleton. The skeleton of this guy will look like this. I think this thing is confusing. Let me draw a straight line to separate them. I hope it's now clearer, because I'm looking like it might be confusing some students and I'm putting the arrows. Now look at this. So butane. So what do? We can kink at the beginning, then draw a straight line again, like this. So what does this tell you? So we have a carbon here, 2, 3, and 4 carbons. Exactly. So this is the only place you can kink, okay, to show that, that kink for skeleton is to show that each of the vertices will represent a carbon, right? Then number 5, for 5 carbons, we're going to have C5H10 minus 2, that's 8, H8. Exactly. You just be using the formula to get it, for those that don't know how to do it. So that's going to be CH3, this is CH3, okay? I like to write it this way. Okay, you might see CH3, CH2 in some textbooks. All right. So CH2, and there's also CH2, 1, 2, 3, and CH2 and C triple bond CH. So this is what it's going to look like. And for that reason, we are going to have a structure that looks 1, 2, let's see, 1, 2, 3, 4, 5. All right, so this is going to look like this. Either way, I could also start it like this, okay? I could also start it like this. So if I do it this way, it's still the same. 1, 2, 3, 4, 5. Exactly. So I just turned it, okay? All right. So this is pentane. So what you should do is try to draw the other structures and to see for yourself. And if you are not sure, to vet what you did, you can send your answers to me on that WhatsApp number. I'm going to check if you are correct. So, but of course, let us build it up together. Now, so that is that about the homologous series. Now, let's quickly migrate to naming. So how do we name? Now, I have covered many, I've covered videos on naming alkynes, on naming many organic compounds. There was even one where I named 50 organic compounds. So make sure you see that video. But of course, here I will still teach you how to name alkynes. Now, what I will primarily teach you that is different is, what if we have alkene and alkyne in a molecule? So that confuses students. I'm going to show you now. But first, let's name alkyne. Now, it follows the same principle as we have been having before, which are identify the longest carbon-to-carbon chain, identify the longest, identify the parent chain. That's the longest carbon-to-carbon chain. Is that okay? Identify the parent chain. Now, when you are after identify the parent chain, number such that the functional group, what's the functional group? The C triple bond C, right? Gets lowest possible number. Gets the lowest possible number. Okay, so when you number, you should number such that this triple bond has the lowest possible number. Then, of course, so substituent, so functional group has priority over substituent. Is that clear? So then you now follow other principles by writing number first before the substituent, then the family name. So let's try to name something like this. For example, let's name this guy CH3 C triple bond C CH2 C CH3 C H. Now, for those that seem confused when people write things like this, one way to help yourself is to stretch it out, okay? For starters, when you see something like this, you can open it up, open up the molecule. This becomes CH3 bonded to C, then triple bonded to C again. Are you following me? Then, so we are here, then single bonded to H, then there are two hydrogens here, three hydrogens. Then, of course, C, then single bonded to H, and then another, so there's a methyl group, there's a substituent there. And of course, there's CH2 again, two H's, then there's CH3. Okay, every other molecule I'll name here, I will not open it up, okay? Or maybe I will just draw the opened up this thing form. But this is how to help yourself. You can open it up, then it helps you to see everything clearly, okay? So with that, we can identify the substituent already. Now, remember which direction will give this guy the lowest number. If we number like this, this substituent will get number 1, 2, 3, 4, 5. We'll get number 5. If we number like this, the substituent will get number 3. But is the substituent our target? No. The functional group is our target. So we go like this, where this functional group will get lowest number. So we go like this, 1, 2. So we've gotten 2 for our functional group. Then this guy is going to be on 5. So we have 5 methyl, 1, 2, 3, 4, 5, 6, 7 hept. 7 is hept, right? That will be hept. Now, the triple bond is on carbon 2. So hept 2-ine. Hept 2-ine. Is this clear? Hept 2-ine. So that is how to name this guy. All right? Now, the other way you can name it is to say, see, 5-methyl. This is old, actually. This name that I gave you here is the post-1993 naming system. After the 1993 naming system, they came up with this. But before that was this one where they used 5-methyl, then 2-heptine rather. Heptine. So this is the old name. Okay? So I prefer to write this, okay? Now, what if we have something that looks like this? So let me open this one up already for you. So see this. CH3. So let's say you have something like this. How do you name? Now looking at this, what's the longest carbon to carbon chain here? Now if you go here like this, you would think you have seen the longest carbon to carbon chain. But in fact, no. If you look at this, there is double C's here, right? There are double C's. Oh, there are 2 C's rather. So here is ethyl. So this is ethyl, this is methyl. So you go in direction of that ethyl. So you go like this. So the longest carbon-carbon chain, this is actually a substituent. The longest carbon-carbon chain is like this, that follows this kink. Is it clear? So with this, we can now name. So, but of course, If we go like this substituent, we have a low number. So which direction are we following? This direction, because this direction gives these guys the lowest number. So it's going to be 1, here 1, here on carbon 2 is the first triple bond. We have 3, 4 is the next one, and 5, 6, 7, 8. Okay, so 7 and 8 are hidden here. So we have our substituent methyl is on that guy. So maybe let's add one more substituent. Let's add like Cl here, chlorine here. So we have 6 chloro, 6 chloro, 6 methyl, 6 chloro, 6 methyl. Let me shift it down. We have 6 chloro, 6 methyl. Now you have your, how many carbons do we have? We have 8 carbons, right? So that will be oct, right? Now we have 2 triple bonds. So if we have 2 triple bonds there, what do we have there? It's going to become what? Di, right? Diene. So it becomes octa. What numbers? Which numbers do we have there? On which carbons do we have the triple bond? Carbon 2 and carbon 4, isn't it? So it becomes octa 2, 4 diene. Di, then ine. Is it clear? 6 chloro, 6 methyl, octa, 2, 4 diene. So this is how to name this guy. Now what if we have, I'll treat one more before we now treat where we have double and triple bond. So let's name this one together. Once I draw the molecule, try to name it yourself. Let me open up in 4, so I have this. So when you have something like this, how do you name? Now, your target should be the triple bond position. Let's number in this direction first. If we go like this, whether we go like this or go straight, it's the same. So if we go 1, 2, 3, 4. So the first triple will appear on 3, 4, 5, 6, and 6, 7, 8, 9, 10. Okay? If you come like this, it will be 1, 2, 3, 4. So the first triple is appearing on 4 in this direction. So we are picking which direction? This direction. You see, I did not concern myself with the position of the substituent at all. Yes, because the reason is our functional group is the priority here. All right. So we now go in this direction. In that case, this the first set of substituents to fall on carbon 2, which are chloro and methyl. Then here we have on carbon 6, 7, 8, 9, 10. So on carbon 8 and 9, we have the remaining substituent. Notice I am circling out my substituents so that I would have separated them from the main chain. All right. So we start with, in alphabetical order, we start with the bromo, right? So that will be 8, 9, 9, right? So that will be 8, 9, 9. Try what? Oh, now because T comes after C, chloro is the first. So we have methyl, we have chloro, and we have bromo. The reason why I wanted to write this first was because of B, but it should be, if it was one bromo, it should be, if it was only on 8, for example, is that 8 that will come first. It will be 8 bromo. You understand? It follows alphabetical order. So for here we are using T first. So this name changes. So we are following with chloro first. C comes first. So that becomes 2 chloro. Keep in mind, it's not in numeric order. You notice here that it is also 6 chloro first before methyl. Okay? So this become 6 chloro, 2 chloro, 2 methyl. Both of them are carbon 2, carbon 2. 2 chloro, 2 methyl, then 899 dash 8,9,9 tribromo rather. Okay, tribromo. Now how many carbons do we have? 10 carbons. Okay, that will be dec, right? Dec what? Carbons 3 and 6 contain our triple bond. So dec 3, 6 deca 3 or dec 3 dec 3 or deca 3 dec 3. No, it's deca because here we used octa, right? Okay, it's deca 3. When there is more than one number like that, when it is more than one functional group there, we do it that way. Is that okay? We do it that way. So it will be tribromo deca 3, 6 diene. Exactly. So this is the name of that molecule. 2 chloro, 2 methyl, 8,8,9,9 tribromo deca 3, 4 diene. All right. Now, what if we have a structure that has both double and triple bond? A molecule that has both double and triple bond now. Both double and triple bond. Now this one is very simple too. Just watch. Now what students don't understand is that for multiple bonds generally, you only pick one as more important when you have to make a choice. In a case where either one falls on the same side, let me explain. Number, the way you should number is such that number in such a way that either double or triple bond, either the double or the triple bond, have the lowest possible number. Okay, but in a situation where you have to make a choice, but where you have to make a choice, give double bond, okay? Give the double bond C, give it the lowest number. Do you understand now? Now, where you have to make a choice, you give the double bond the lowest number. But you see, I will show you, I will draw several molecules now, several structures now, and you see whether, okay, no, let's use this one. Let's use this same guy. So firstly, when you have double and triple bond, their general name should be enines, okay? They are not called imines. No, not imines. It is enines. So this already tells you the positioning. So N before the double bond before the what? Triple bond. N9. Is it clear? All right. So now let's start with, in fact, let's name these two molecules. But I will now change this one to double bond here. And change this one and leave this one as triple bond. Let's name this molecule. So here we have a double bond. Okay? So if that's the case, then this one too, we'll do it that way. We'll leave this one. Let's put a double bond here. Let's put the double bond here. Okay? Now, we will know whether we have to make a choice here or not. Okay, so you will notice that the position of the substituents did not change, right? So these substituents are not changing. Now our functional groups are the ones that have changed. Our functional groups are the ones that have changed. Okay, so let me clean the name altogether. Watch. Let's name this first guy. Where are our substituents? This guy is still our substituent. This guy and this guy are our substituents. Okay, so here, how do we name now? I said that you should number in such a way that either the double or triple bond have the lowest possible number. But where you have to make a choice, give the double bond a lowest number. Now see, if you number in this direction, double bond takes 2, triple bond takes 4. Is that clear? If you number in the other direction, triple bond takes 1, 2, 3, 4, takes 4. So that direction is not even, this question is even quite simple. I'll give you a question that the type they give in exam that confuses students. This one is very simple. In this direction, if you come like this, it doesn't even make sense. What you might be thinking is that we're supposed to give triple bond priority because, so for which reason we should now name this one. We should name this one from this direction. But already you should keep in mind that this one will fall on 4. Triple bond will be 4, and this one will take 5, 6. This one will take 6. So that's a very big number. So the lowest possible number for both bonds is in the direction that gives the double bond the smallest one. Is it clear? So we are going in this direction. So our molecule becomes 6 chloro, 6 methyl, oct still. Let me bring it down here. Oct. Now watch. Oct. We have 3. You know that it should go double bond first, right? Double bond first, then before the triple bond. So oct. Now our double bond is on carbon 2. Sorry, carbon 2. We are going in this direction. Carbon 2. So oct 2 and is it correct? Oct 2 and then triple bond is on carbon 4 so we have oct 2 and 4, right? Is that clear? Just is as simple as that. 4-ine. And that's the name. Is it clear now? Oct is 8 carbons, yeah? Now where's the position of the double bond? On 2. So 2 is the choosing of the position that confuses students. Let's go to this one. See this one. If we go like this, we have 1, 2, 3. Triple bond falls on 3, carbon 3, 4, 5, 6. Double bond falls on 6. If we come like this, we have 1, 2, 3, 4. Double bonds carry 4 carbons. So here, you would think that we were biased by giving single bond number 2, that we were favoring double bond. We are favoring them both. Because if we come in this direction, this one will fall on 4, 5, 6. Okay? So this will be, let's go again, We have 1, 2, 3, 4. Sorry, 4. So double bond will fall on 4. This one will be 5, 6, 7, 8, 9, and 10, of course. Now, my point is, if you come in this direction, double bond will take 4. The number will be 4. Triple bond will take 7 because it will fall on carbon 7. So 4, 7 is higher than this direction, which is 3, 6. So we'll follow the direction that gives them both lowest possible number. The only case I'm saying here that you have to make a choice is if you go in this direction, let's say for example, you go in this direction, you will get the same number as going in this direction. Let me explain again. If you go rightward, you will have the double and triple bond will have the same set of numbers in both directions. So let's say it is 1, 6 in this direction and 6, 1 in the other direction. Then that's where you now have to make a choice, where you now favor double bond. You will now go, if 1 will be for double bond, then go in the direction that gives 1 to the double bond and 6 to the triple bond. Is that clear now? So that's where it comes in. But in this case, give it number in the direction that gives either of them lowest possible number. Because if you go, it's not either of them, it's supposed to be both of them, okay? If you go in this direction, it will give triple bond 3, to give double bond 6. If you come in this direction to give double bond 4 and 7, that's greater than 3 and 6. So we're using 3 and 6. So our name becomes the same guy. We're using this direction. That's 2-chloro-2-methyl 899 tribromo dec. Now 3. Now what? Dec. We have to write N first. You have to write double bond first, right? So dec 6 and 3 ion. Is it clear now? So that is how to name that molecule. Now let me draw an example for what I just gave you now. If I have something like this, for example, look at this. This is double bond here. And then we have triple bond here. So we have 1, 2, 3, 4. And 1, 2, 3, 4. Yes. So this is the type of scenario I was talking about. Now, what if you are told to name this molecule? Now, if you go in this direction, you will have carbon 1, 2, 3, 4, 5. Come in this direction, carbon 1, 2, 3, 4, 5. Now, if you want to name in this direction, this carbon, this double bond will fall on carbon 1, triple bond will fall on carbon 4. Make sense? If you want to go in this direction, double bond will proceed from carbon 2. Remember, it's where the carbon double bond proceed from. The carbon proceeds from that will count as the owner. So this guy is the owner in this direction. Carbon 1, 2, 3, 4. So 1, 4. Now, if you come in this direction, it will be 1, 2, 3, 4 still, because this double bond will be 4. So it is in this direction you now have to make a choice. So you should choose. Which direction should you choose? This direction. Why? Because if you come in this direction, this one will take 4, this one will take 1, this one will take 4. If you go in this direction, this one will take 1, this one will take 4. So choose the direction that will give the double bond the lowest number. Do you now understand? It is when you have to make a choice where both of them we have both numbers the same, both numbers in opposite directions, equal numbers in opposite direction. Then that's where you should now give the priority to the double bond. So this will now be 1, 2, 3, 4, 5. That will be pent 1. So pentene, exactly now, pentene 4 ion, or pent1 in 4 ion. Exactly now. We don't even need put 1, so that's pentane 4 ion. Pentane 4 ion. So that's the answer. So that's how to name alkynes. Exactly, alkynes. Now let's move on to the synthesis of alkynes. The synthesis of alkynes. Let me clean this place. Let me rub it. No, let me just close that. Right now, so how do we synthesize alkynes? So there are two techniques I'll discuss with you. We have the industrial technique and the general, would I say laboratory technique now? So the one that is used industrially, there is the synthesis we want to discuss now. Now, the first one is the industrial method, okay? Industrial process. Now, the industrial procedure is to dissolve, react calcium carbide with water, okay? So calcium carbide plus water. Okay, so where does the calcium carbide actually come from? It comes from coke, of course. So that's carbon from coke. So, and you know coke is from coal, right? Carbon represents coke rather. So coke is from coal. Let me charge this thing. So plus the calcium carbide. Where would the calcium come from? To come from limestone, right? quicklime rather. Quicklime that comes from limestone. So this quicklime, it comes from limestone. That's CaCO3, CaCO3, right? So these two, when you heat them together at high temperature of about 200 degrees Celsius, so what you produce is calcium carbide. Is that okay? So when you now produce your calcium carbide, you pass it over water, you react it with water, what you produce is what? Ethine. So of course it will revert to this, the other minor product will be like this guy back, but this is the major product, ethine. So this is the industrial procedure. So let me quickly pause this thing. So let us continue. So I said the industrial process is where we react calcium carbide with water. Now, so that's how to produce ethine, okay? But this one is for ethine that I said I want to, they will now speak generally, okay? But another way to produce ethine, another industrial process is by reacting controlled so if you react calcium, if you react what's it called now, methane, you react methane with water under very high temperature, very high temperature. Where is it? Sir? No problem. So I was talking about industrial process. So under controlled, so the second process is methane. You react methane, CH4, with water, with oxygen, controlled oxidation, okay? Controlled oxidation, okay? And at very high temperature, with very high temperature, as high as 1,500 degrees Celsius, okay? You are able to synthesize a thing as well. So with oxygen, you produce C2H2, plus carbon monoxide plus hydrogen gas. So if you balance this reaction, how do you balance this reaction? Try to balance it, okay? You have CHO, who are these people? Help me unplug it. Okay. No, I'll leave it. They might soon restore power again. So we have CHO. So C is 1 here. H is 4 here. I'm trying to balance this, okay? So C2H is 4 here. O is 1. It's very simple, okay? Bring 2 here. So it becomes 2. H has become 8. Okay? So to balance that guy here, you put 4. You put 3 here. 3 times 2, 6 plus 2, 8. So how about the oxygen? Oxygen is 2 here, it is 1 here. If you put 2 here, carbon has become 4. Oxygen has become 2 here. So with carbon becoming 4, if you put 4 here, try to balance it, okay? I've showed you a video on how to balance chemical reaction. You can send me the answer on that WhatsApp number, okay? I don't want to waste time balancing it, okay? So I put 4 here. Is it balanced? No. So try to balance it, okay, and let me know what your answer is. Try to balance it. So let me just remove this. But these are your products. I remember that these are the products, carbon monoxide and hydrogen gas. Alright, so balance it for me and let me see the reaction. Then if you do make a mistake and you send it to me on that WhatsApp platform, I will correct it. I would have even done it by then. Okay, so see, Let's now go to the general procedure for alkynes generally. Alkynes, synthesis of alkynes, general process of synthesizing alkynes. So the general methods now, general methods of producing or production of alkynes. So the first method I want to discuss, which is the primary method. Before we do that, sorry, there are two types of alkynes that we should know. There are two types of alkynes, okay, which remains consequence to this course. Number one is the terminal alkyne, okay, they are very important, terminal alkyne, and they are the ones that we'll be talking about the most, terminal alkynes. Then the second one is internal alkyne. Internal alkynes. A terminal alkyne is one that has the carbon-to-carbon triple bond at the end. So this one is bonded to H, so this is a terminal alkyne. Okay, this one is bonded to R, to another alkyl group, but as far as this triple bond is at the end, and that's terminal alkyne. Then an internal alkyne is where you have R, C triple bond, C, then to another alkyl group. So this is an internal alkyne. The triple bond is in between, is in the middle of the chain of the molecule. All right, so now the general method of synthesis, the first one includes dehydrohalogenation. Now, what does this mean? It's very simple. You remember in alkene, please, if you have not seen that video, make sure to see it. When we dehydrate alkene, dehydrohalogenate alkene, what do we get? We get an alkane. So it means that for these ones, it will be a two-step dehydration. Two-step dehydration. Remember, for alkenes, if I wanted to dehydrate this alkene, for example, dehydrohalogenate this alkene, let's say there was a Br here. So what will happen? It will follow ZZ's rule, and then of course, this guy, the catalyst that will be used is alcoholic KOH. But remember that alcoholic KOH, yes, and then the base will remove this guy, and then we'll remove the hydrogen rather to deprotonate this guy. Because the guy is very slightly acidic, it will deprotonate it, then the leaving group will leave, right? Do you remember the mechanism? All right. Then to produce an alkane, right? Now, in the case of alkyne, it means that it's going to be two steps dehydration. So what does that mean? It means that the molecule that want to dehydrate must have a dihalide. Exactly. Dehydrogenation of alkyl dihalide. A dihalide means two halides. It must have two alkyl groups, right? It must have two alkyl groups. Now, how does that happen? So I could have something that looks like this. For example, I like to use this. Now, I like to use a terminal. Okay, we want to synthesize it. So let's use this guy that has Br. If we are starting with alkane, okay? That has Br here and Br here. Now, you must know what we call, I've told you this before, so geminal and vicinal. Now, the word geminal is from the word geminus, which means neighbor, okay? No, geminus means geminus, I think neighbor, then vicinal. No, vicinal is neighbor. Vicinal is the word vicinus. Vicinus, which means neighbor. I can't really remember this thing. But I think I've told you in the former video, I've forgotten now. I told you in the alkene video, geminus means the same or so. Okay, more like the easy. I told you this also. Easy, where this one means entgegen. I still remember this one. This one is Latin. This one is German. German for same, on the same carbon. Okay? No, I'm on opposite, different. This one is different. Why is this one is Zusammen? Zusammen means on same carbon, okay? On the same carbon. So looking at this one now, this germinal to geminous means same carbon. So if I say germinal alkene or germinal dihalide, germinal dihalide means the halides are on the same carbon, but vicinal dihalides are dihalides where the carbon is on different, the halide is on different carbon. So just know, germinal, same, vicinal, side by side, right? They are neighbors. So this, would this be a germinal or a vicinal? This will be a vicinal. Why? Because this bromine is here and this bromine is on the next carbon, the adjacent carbon to it. Is that clear? So please remember that, okay? So we want to use a vicinal dihalide here. Now when you use a vicinal dihalide like this, there are vicinal dihalides that can form terminal alkene, okay? Terminal alkyne. But with this one will form an internal alkyne rather. This one forms what? An internal alkyne. See, how will I know that it's going to form internal or terminal? Just look at the position. Once you see the position, you'll be able to tell. Okay? Now, another thing you should know is that I'm going to draw this thing out in full structure for people that don't normally understand with skeleton. So I'll still draw it when I want to show you the mechanism. Now, another thing you should know is that there is also a reaction where this triple bond I want to form here can actually shift to the end. Okay, it's called the Zepa's reaction, but I will not be covering that here. And you might not likely even come across it, okay, for even your A level. But just know that there's also a reaction known as Zepa's reaction where that triple bond can move here, okay, can move to the terminal. But here, I want to show you how to form an internal alkyne and how to form a terminal alkyne. So we're going to use this one to form an internal alkyne. So this guy, we're going to be reacting it. It's going to be a two-step reaction. So in the first step, you can take the first step with your common KOH, alcoholic KOH or NaOH, any strong base. Because remember, for alkene, we use any strong base, right? KOH or NaOH, right? Now, so the first thing to do is that it will deprotonate this guy. Of course, this guy is going to have the H here. It gets deprotonated, then the leaving group will leave, right? Okay, and this guy too deprotonates, the leaving group leaves. But I want to start with the actual reagent, okay? The actual reagent that we use for this process, because it's going to be a two-step process. The actual reagent that we use is called sodium amide. Sodium amide. Now listen to me. Now the reason why I did not use that again is because I don't want you to be confused, so that you'll not be thinking there are two reagents you are using. Okay? We'll use just this reagent from start to finish. And then I'll now show you why I wrote that first one. Now, sodium amide is just NaNH2, right? But I would like to write, when this guy ionizes, okay, I like to write the ionic form. When this guy ionizes, it's going to give us NH2 is the, I'm going to write it the Lewis structure with the Lewis dot diagram, Lewis dot structure. Now, the reason why I'm writing it is so that you see that this guy is the active guy, okay? Then of course we have Na plus, right? When this guy ionizes. So that's what I'm going to have here. I have NH2 with the dots, the electrons, with the electrons, then sodium, Na plus. Then you might be thinking, why did I not write this here and this here? I wrote it like this because this guy is coming to come and do the job. Exactly. All right. This guy is a very strong base, right? So now, what does it do? This very strong base, very, because it's actually very strong. Yes. So now what does this do? This guy is going to come close to this guy. So this guy has hydrogen here and bromine here. It will come and, you know, this is where we draw the diagram, right? It come and deprotonate. Deprotonate means to remove the hydrogen. Once it removes the hydrogen, then the bond on this one, right, will cleave here. So once it deprotonates the hydrogen and the bond cleaves, let me put the Br here. Let me put the Br here so that I put the H here. So it deprotonates this guy. When it removes this guy, the bond will come and form a double bond here, and this bond will cleave to the bromine. So this is a leaving group, right? It will leave. Once it leaves, the first product that it will form will be an alkene rather, that looks something like this. So already you can tell that, right? To look something like this. Make sense? Now, actually, because there is a double bond here, there is a 1, 2, bromine is attached here, hydrogen is attached here. What will happen is that, now that is how the Zippers reaction actually starts too. Now, what will happen is that this bond will actually fall on this part first, okay, because it cannot come here yet, okay, because of these two that are already bonded here. So to come here first, it is when this reaction has now taken this guy up again that the two pi bonds will now form here. Is it clear? All right. So, but this will be like an intermediate product. So, but let me not draw the intermediate product then. So that this same guy will come here and also deprotonate this guy. Another NH2 still in the reaction will come, deprotonate this guy, to deprotonate this guy, and the leaving group will leave, right? The leaving group leaves. The leaving group leaves. So what happens? Then this bond will now be used to form a pi bond here. So once it's forming a pi bond, then you now have a molecule that looks like this. How many carbons? One. All you have to do is just count how many carbons you have. 1, 2, 3, 4, 5, right? So we have 1, 2, 3. So know that there's a carbon here and there's a carbon here. Makes sense? So this is what will now form eventually. Now, so this is the case, okay? This is the case. And why is this the case? Is because this guy, okay, I told you it will deprotonate this guy here and deprotonate this guy. But also, I forgot to put the fact that it happens in liquid ammonia, okay? Take note of that fact. It happens in liquid ammonia. Now, this guy will remove this guy. I'm showing you this for those that really don't know how to write, what's it called now? That don't understand mechanism. This guy will take this guy up. After it removes it, this bond will fall here. But I told you to know, because of for internal carbons, for internal this guy, for internal alkynes, that's how Zippers reaction. You should already understand now that if this double bond falls here, see what will happen. It will not be stable, right? Because there is already Br and hydrogen attached here. So what it will preferably do first is to form here. So before it now cleaves back here. Is that okay? So, but because it's a strong base, it does the removal almost immediately at the same time for vicinal dihalides. So to remove it to form the internal guy at the same time. Is that okay? So the shifting process for Zippers reaction is almost the same. Once this guy forms here, this double bond will also shift here to form an alkyne. But I said I will not talk about it. So that is the hydrogenation for you. Then what if it was a germinal halide? Germinal dihalide. For germinal dihalide, the process is the same in as much as both are on one carbon. The process is the same. But one thing with germinal dihalide is that, for example, if this dihalide is here, if this dihalide were here, for example, let me use this guy. My dihalide is here, Br and Br are on this guy, for example. So what will happen? Okay, let me use another compound. Let me use like ClCl. Okay, because I've used Br there. Now, what will happen here? Now, usually, terminal alkyne is the one that will be formed in this case, where I have my NH2 and the negative charge, my Na plus, both immersed in this guy. So what will happen is that this guy will approach. Now watch. Here's the key. When this guy approaches, what does it do? It will deprotonate this guy here, and once it deprotonates this guy here, what will happen is that this bond will fall here. The bond with, there is going to be 1, 2, 3 hydrogens around here, right? 3 hydrogens. So once it deprotonates it, this hydrogen will fall on this guy. The bond from the hydrogen, rather. Let me show it in full. I have this. So I have 1, 2, 3 hydrogens like this. Normally, right? So this guy will deprotonate one like this. Deprotonate and remove this hydrogen. So this bond falls here so that this leaving group leaves. Is that clear? Then deprotonate another one. Maybe this one, for example, deprotonate this guy. This bond also falls here. Do you understand now? So for that reason, then this leaving group also does what? Leaves. So once the leaving group leaves, what will happen is that I showed all the mechanism in one step, okay? I showed all the mechanism in one step. So once it deprotonates this guy, this bond will fall here because it will take up this hydrogen and this guy will leave. Then what will happen is that these two bonds will form here. Now, there is one thing I want you to notice. I want you to take note of. Now, with terminal alkynes, so usually, there is one hydrogen left here, okay? There's also one hydrogen left here. But the case is that when you react with this very strong base, okay, it goes on to still abstract this hydrogen. It will still abstract it. So it will still come here, approach this gentle guy here, and do what? Remove it. It will remove this hydrogen. Okay? So, and in that case, it forms an alkynide. An alkynide ion. Now, this is very useful if what you wanted to do was alkylation. I'm going to show you what alkylation is in the GP. So if the process you wanted to carry out was alkylation, now this procedure is very okay, is advantageous, okay? Because this guy is a very strong base, what it will do is that it will keep deprotonating all the hydrogen from where it is removing from. For example, it has removed 2 here, right? It was remaining 1 hydrogen. What to do is that it will remove this 1 hydrogen again. Then it will now form this alkynide that looks like this. 1, 2, 3, 4. With 2 electrons. Okay? So when it forms this, to now form our stable guy, to form our stable alkyne, you have to now react to this guy with the reaction should happen in a protic solvent. Protic solvent is solvent that has proton inside, okay? So if that happens in a protic solvent, so for example, maybe in an acidic, like in water, for example, acidified water. So what will happen is that you have this guy, hydrozonium ion, for example, or H+. You could use H3O plus or H+. Then those guys, that one will now protonate that guy back so that you have your stable alkene. The hydrogen returns. Do you understand? So I'm not showing it here. So this hydrogen has returned. As in, I'm trying to show you that this guy is so strong a base that it keeps deprotonating. It keeps deprotonating the molecule. Okay, so it will make sure that it has moved all the hydrogen on that guy. So if it forms alkynide ion, okay, I told you that procedure is advantageous for alkylation. But if what you just have to form is your terminal alkyne, then this becomes your answer, your terminal alkyne. Okay, and what is this guy? 1, 2, 3, 4, 5. This is pentyne. Okay, my molecule is even wrong. Okay, my structure is wrong, right? I've already told you that before here. So this way you should draw it. Here, you go like this. Is it clear? So it should just go up. You should already know why I said it's wrong, right? Because it should be a linear molecule here. So here too, what I will have is this. Linear molecule. Do you understand now? Alright. So, but if it was alkylation that you wanted to perform, what is alkylation? It's just a process of building up alkyl groups, building alkyl groups to make a large, maybe alkane or a large molecule, okay? So what will happen is that this guy is very reactive, right? Alkyl there that you see there is going to be very reactive because an ion, okay? Ions are reactive. So you have something that looks like this. Alkyl. Now this guy is very reactive, so what he can do, what he can possibly do is that if you react it with any alkyl group, okay? Any alkyl group, maybe an alkyl halide again, what it do is that it can take this alkyl group. So for example, maybe it's methyl, then the methyl will add on to this. Now, if this base is still present, it can deprotonate again, and then the methyl will keep adding, okay? I mean the group that is abstracting from here, maybe it's ethyl or methyl, for example, that is taken from here, will keep adding to it, and then you have what looks like this. Do you understand now? So that is the reaction. Okay, this is for alkylation. So that's why I said this thing is useful if it was alkylation, but it's not so useful if it were just your terminal alkyne you want to form. You need to put it in a protic solvent so that it will be protonated back by that protic solvent, and then you get your terminal alkyne. Now let's go to so that procedure, the procedure I just explained now, is dehydrohalogenation. So I've explained two steps, two processes now forming alkyne, this one and this one. Is that clear? All right, now let's move on to this way you should draw it. Okay, there's a carbon here, then there's R group, like that, depending on the complexity of that guy. So that's that. So that's how to form alkyne. Now let's talk about the physical properties of alkyne before talking about the chemical properties. Let me clean here. Now, what are the physical properties of alkyne? Now you should make sure to listen, okay? Listen at this point. What are the physical? Then, just in case you ask, what mechanism is this? This is an E2 mechanism, okay? Because it's elimination, right? E2, that is elimination by molecular. I've told you this before. Watch my video on this thing. I also introduced in that 30 terms. Elimination by molecular reaction, okay? And of course, alkylation is not that. Alkylation is SN2. Alkylation, there is SN2 reaction. All right. Now, I said SN2, for those that don't know, means substitution nucleophilic. Okay, now physical properties. Let's talk about the physical properties. Now, what are the physical properties of alkene? The physical properties of alkene are, number one, or alkynes rather, of alkynes. Number one is that they have low polarity, okay? They have low polarity, okay? So, and because of their low polarity, very low polarity, they are insoluble in inorganic solvents, like water, for example. Insoluble in protic solvents like water, or inorganic solvents like water, but soluble, rather soluble in organic solvents. Okay, organic solvents like ether, benzene, and benzene derivatives, toluene, phenol. Okay, benzene, toluene, carbon tetrachloride, CCl4, right? Carbon tetrachloride, etc. Okay, all these guys. Now, that's about their solubility. Okay, now, actually, their boiling points. First, their solubility also decreases, in fact, with the molecule, the size of the bulkiness of the molecule. Okay, Now let's talk about their boiling points. Their boiling points are generally low, okay? Generally low, but increases with number of carbons. So it means that as you go down an homologue like that, so for example, ethyne we have a lower boiling point than butane. Butane we have a lower boiling point than nonine. Nonine we have a lower boiling point than dodecyne. Do you understand? That's carbon with 12 molecule with 12 carbons. So that's the point, that it increases. The boiling point generally is generally low, but increase with number of carbons and decrease with degree of substitution. So the higher the substitution or branching, okay? The higher the substitution or branching, comma, the lower the boiling point. So once the molecule is highly substituted, then it is going to have the boiling point to be lower, or it is branching, okay? It is not a long straight chain. It's going to have a lower boiling point than its corresponding straight chain. Now, how about now, you know that thing I told you from the beginning about the proportion of carbon to hydrogen. So because the proportion of carbon to hydrogen is high in a thing, high proportion of carbon to hydrogen, high carbon to hydrogen ratio makes them burn with luminous sooty flame. So they are used for lighting, okay? They are used for lighting because they burn with luminous sooty flame. Is that correct? Their flames are luminous. All right, so that will be it. Of course, this is not a physical property though, but terminal alkynes are labile. Terminal alkynes, they are said to be what? Labile. What does labile mean? It means they are what? Acidic. Labile or what? Acidic. It's going to, when we start the chemical reactions now, we are going to talk about it. Now, let's talk about the chemical properties now. Chemical properties or the reactions. That's basically what we mean by chemical properties. The reactions of alkynes. The reactions of alkynes. Let me list the reactions there, then I'll clean that place to show you the reactions. The first reaction we'll talk about will be let's start with the simple one, hydrogenation. Hydrogenation. So it's just two-step hydrogenation, just like we saw with alkenes. You see, to remember the reactions for alkyne, just look at the connection with alkene, and you'll be able to remember them. Hydrogenation, then we'll do let's first do hydration, then we'll now do hydrohalogenation, then we'll now do hydrohalogenation, then we'll now do, what's the next one we'll do now? Hydrohalogenation, then we'll do hydroboration. You see, I remember them with just this many B's, okay? We have done hydrohalogenation. That's the opposite of that. So then we'll do oxidation. Of course, there's also combustion reaction. Oxidation. In this case, we'll be seeing ozonolysis and permanganate oxidation. Then we'll see, if I remember any other one, we'll consider it. Okay, so let me pause it first. Now, we'll start with hydrogenation. Hydrogenation. Now, so what do we mean by hydrogenation? Remember that if we wanted to hydrogenate alkene, very simple, we go in one step, right? The same way, it's very similar to alkenes, okay? So the hydrogenation of alkynes is very similar to alkenes, only that this one go in two steps, right? To first hydrogenate the first time, then we need to hydrogenate another time. Is that clear? To break the bond finally. So let's say we have this guy now. I want to break 1, 2, 3, 4. This is butane, okay? So this is butane. So by the time we break the first bond here, by the time we hydrogenate, okay, we break the first bond, it's going to attach 2 hydrogens to it. Now, well, again, keep in mind that it takes place in the presence of platinum or palladium catalyst or nickel catalyst. You remember, we did that in Sanderson's reduction. So this is also called the reduction reaction. Okay, reduction reaction. So when you react the first guy, make sure that this guy is supplied in excess, right? So when you react the first time, you break the first bond, it's going to form this, right? The molecule that looks like this. So, and of course, you react the second time, it forms this. You react the second time to form this, right? 1, 2, 3, 4. Okay. So now, let me show you in full diagram. What I mean by this is this. So the first time you react it to break this first bond. Now there is something. Remember, if it was an alkene, it will add. We'll call it syn addition. Okay, syn addition. So in the first step, when the syn addition happens, how does the syn addition happen? This alkyne floats on the metal, and then what it does is that it breaks the bond. The metal is able to break the bond such that the hydrogen can attach on the same side. That's what we call syn, same side. I've mentioned all these terms before. Same side. That E and Z conformation. The one I also mentioned, geminal, vicinal. Don't misplace them, okay? This one is syn addition for alkenes. So here it will form in the first step, it's going to form a cis alkene. So what does a cis alkene mean? Watch here. Once it breaks this guy, this is what you will have in the first case. You have our CH3, CH2. Now watch. This guy will form C double bond, then CH. Now this is our former H. The new H will be here, and another new H will be here. So what do you notice? It formed on the same side. So this is what we call cis. Okay. So this will be cis 1, 2, 3, 4. Cis butene. Is it clear? Butene because it is on the terminal carbon. Is that okay? So it is a syn addition reaction. Keep in mind, it is also an addition reaction. Let me show you this. Hydrogenation, addition, hydration, addition, halogenation too. Okay, I didn't even mention that. Number 6. Those are the 4 steps that we should even consider. Halogenation is the same. Before now, hydrohalogenation. Is that clear? So halogenation, addition, hydrogenation, hydrohalogenation, addition, hydroboration, addition, oxidation is also addition, in fact, because it breaks the bond. I will show you. Any reaction that breaks the bond and adds to it is addition reaction. Okay? So then we'll now talk about combustion reaction. Combustion reaction is just general and simple. So that's why combustion reaction. Now, so I said it's cis addition. Then what will now happen? This one will now, on further reaction, what will now happen? It will come here and break the second pi bond again. Once it breaks the second pi bond, then it comes here and forms this. Then you have the new hydrogen that were formed, and the new hydrogens are added to them like this, and like this. Is it clear? So this is the final product, which is what? A butane. Okay? It forms the normal butane. Is that okay? Normal butane. Now, what if, okay, so that's it. That's it for hydrogenation. That's it for hydrogenation. One other thing that you should know is that what if I wanted to form a trans product? Now, if I want to form a trans product for the alkene, if I want to form a trans product, what will happen is that this reaction will take place with our hydrogen, okay, hydrogen gas, but it will happen, the reduction will happen in a normal metal, what's it called now? Neutral metal, okay? This is a neutral metal now. Now, when you have a neutral metal is a radical, okay? It's a radical, so it's very reactive. So because of that, so it's going to have one electron, and it is immersed in ammonia as well, okay? It is immersed in ammonia. So what will happen is our butane, what did we start with? We started butane. Our butane is going to undergo addition like this. But what will happen is that it will be cleaved such that this bond will be cleaved such that hydrogen will be added on one side, hydrogen will be added on alternate sides. So you have what looks like this. Now see, one hydrogen will be added here, the other hydrogen will be added here. Is that clear? So then this. So this is the new hydrogen, of course, and this is the new hydrogen, of course. This is the former hydrogen that we have here. Do you understand? So that's what we call it cis. Now it's more noticeable if it were internal alkyne. So for example, let's choose but2-ine, for example. But2-ine, that will look like this. 1, 2, 3, 4. So if it's but2-ine like this, what will happen is that when you react with this, all these guys, what will happen is this guy, we have one C triple bond. So the triple bond, one triple bond has been broken by the hydrogen. So this triple bond, one we had here, double bond, then the other hydrogen we had here. And you have your guy like this. So what does it form? To form the but2-ine, but this is a trans. Is that okay? Huh? A trans. To form a trans. And most importantly, you will notice that what that means as a trans is that both molecules are going, the two hydrogens are on opposite sides. That's what it means. Is that okay? Trans addition. There is syn and there is trans. All right, so that's that for hydrogenation. Let's clean it for the next one, which is hydration. Hydration reaction. So we have hydration reaction. Now, because hydration, what does it mean? It means what? Addition of water. So keep in mind, it's still what? Addition reaction. Hydrogenation means what? Addition of hydrogen. Addition of hydrogen. Or reduction using hydrogen. Okay? So addition of hydrogen. I mean, of course, reduction necessarily means when you add hydrogen to something. Okay? So addition of hydrogen. Now, how does this occur? Addition of water, sorry. Addition of water. That's hydration. Now, how does this occur? Let's still use our terminal alkyne. Okay? No, let's use an internal alkyne now. So that will be like this guy. Triple bond C and CH3. Now watch. Now this guy is reacting with what? With water. Now, what are the conditions for this guy to occur? You should remember that when we were adding water to alkene, there are two conditions: acidification and acidic medium, okay, or an acidic medium. So or oxymercuration. Okay, these were the two possible conditions. Either an acid for alkenes. Do you remember? For alkenes, this process can occur in the presence of either an acid catalyst or oxymercuration, right? That is mercuric sulfate. That is mercuric sulfate. Now, either of both was the case for alkenes, but for alkynes, both of them are what we are going to use. Both of them. So we'll use H2SO4 catalyst and HgSO4. That's mercury 2 sulfate or mercury 2 tetraoxosulfate 6. So by the time you do this, what will happen is that guy, the water is going to be used to break this bond, okay, to break the bond, and it will give us, what does it produce in alkene? It produces an alkanol, right? Because it breaks one bond. Remember, only the pi bond is cleaved. Only the pi bond cleaves. Only the pi bond cleaves. Okay, so since it's only the pi bond that cleaves, and here, what will happen? What will happen is this, that we are going to form what looks like this. Now it has a special name, I'm going to tell you now. Then the water will be added here, for example, and then you have CH3. So this is what is going to be formed. Now what is this called? This is called an enol group. An enol group. So specifically this name, what will be the name of this one? 1, 2, 3, 4. But-2-enol. Is that okay now? But-2-enol. Now, if you remember in that video of introduction to organic chemistry, I told you about one particular type of isomerism. It's called tautomerism. Okay? Tautomerism. So tautomerism will occur here. Why will tautomerism occur here? Tautomerism will occur because this is unstable. In fact, this will be in dynamic equilibrium with but-2-enol will be in dynamic equilibrium with but-2-one. Okay? Now listen, butan-2-one rather, butan-2-one. Now listen. Now the way we draw the equilibrium is such that the butan-2-one is more favored. So this way we draw it. In fact, 70% of what is formed here is what reverts to butan-2-one. 70% reverts to butan-2-one. So what you have is this guy will simply, let me quickly show you the mechanism. It's very simple as well. So what will happen is that this guy, OH, now what will happen is that, there is there are lone pairs on this guy. OH has lone pairs. Lone pairs there. Initially we have double bond, this guy H, this guy CH3. Now, what will happen? These lone pairs, what will happen is that the lone pair, this one was bonded to hydrogen like this. The lone pair will be used to form a bond here. So once that occurs, this bond here will break and come to this guy. So what happens there? Once this guy forms bond here, then you will have what looks like this. I told you that this one is more favored than this, so it will revert to this. C double bond O, then this bond has broken. We have C and CH3. Okay? So there's protonation of this guy again. That's why you have another H here. So what is this? This is butan-2-one. So you see that the butan-2-one is more favored. That's why you see the equilibrium arrow is tilting more towards the butan-2-one than this guy. So this guy changes. This guy is unstable. This is an unstable an unstable product. So that's why it's not the final product. So sometimes you might even call it unstable intermediate. It's an intermediate because it will soon revert to butan 2-ol. All right. So that is the case for hydration. And this hydration follows Markovnikov rule. You have renamed, if you saw that video in alkene, you mentioned it. The Markovnikov rule. Hydration of alkene and alkyne follows Markovnikov's rule. Markovnikov's rule is obeyed. Now, what does that mean? It means that, you know, this guy, I don't want to start going into that detail again, but you know this guy contains OH minus and H, right? Okay, so what happens is that it is this OH minus that breaks that bond. Okay, so OH, the heavy group, will be added to the side with less hydrogen, and H will be added to the side with more hydrogen. Okay, but this is actually more obvious with terminal. Let me show you. I don't want to clean this so that, okay, we shouldn't forget. We are going to, okay, I would like to take hydroboration next. Because hydroboration product, so that you will remember the product. Hydroboration is quite similar in the way it occurs. So I want you to notice something. That Markovnikov rule is not very obvious here. Why? What does Markovnikov rule say? The Markovnikov product is the product that has the heavy group, OH group, attached to the more substituted, the more substituted carbon, or the carbon with less hydrogen. Is that okay? The carbon with the least hydrogen is the one that will have that OH group. But it's not obvious here because this is an internal alkyne. If it was butane, for example, like this. Now, which of these carbons with the hydrogen cleave to? The OH cleave to? The hydrogen will cleave to this guy. Is that okay? The hydrogen will come here. So what we have is, I'm just drawing the skeleton, okay? So this guy will take the OH, double bond CH. So this hydrogen came here, and the OH came here. Do you understand now? So this is the Markovnikov rule, not the reverse. Not the OH will come here and this guy will come here. Exactly. Following the Markovnikov rule, that's why it can still form what? Butan 2-ol when it tautomerizes. Do you understand? By tautomerizing, it will still form butan 2-ol. Is it clear? All right. So that is the Markovnikov product. Now, the second one I'd like to discuss is number 2. Now, number 3 is hydroboration. I said I want to discuss hydroboration because the products look alike. I want you to see something. Now, in hydroboration, basically dissolve your alkyne in borane, any of the any compound that contains borane. So that is let's use a terminal alkyne. We have C triple like this. Okay, so we have our butane. Our butane is going to be masked in, let's use R2BH, comma. Now this guy is also going to be masked in THF, okay? Then, of course, now the reason why I'm treating this is because it gives the anti-Markovnikov product. And what are the factors that enable the anti-Markovnikov product? The presence of a peroxide. Do you remember now? I've told you that before. The presence of a peroxide, there is going to be our base, then there is a peroxide. So hydrogen peroxide in this case, exactly. And then, of course, water. So these are the conditions for that guy to occur. Now you have your borane, your this THF stands for tetrahydrofuran. Tetrahydrofuran is just a particular furan. Furanose, that is 5 carbon chain, right? 5 carbon ring that leaves something like this. But one of the ring is not carbon. 1, 2, 3, 4, 5. So one of this thing is not carbon, it is oxygen. So this is a tetrahydrofuran. So it is this guy, imagine this guy, borane, and these guys are present. So in the presence of this guy, what will happen? The anti-Markovnikov product is formed. The anti-Markovnikov's product is formed. So in this case, where the hydrogen, we are trying to hydrate, that's why water is there, right? So where the OH is supposed to come and cleave to this second carbon, it will not. It will rather come here. So what will happen is that our product becomes something like this. See, this guy takes time. That's why I like the skeleton. So you come here, right, listen, and put the OH on this guy like this, right? I'm sorry. The OH will not stay here rather. The H will stay here, okay? Then double bond to OH here and H here. Is that clear? So this is the way it will happen. That the OH will come and prefer to stay here and this. But of course, what will happen again? Tautomerization. Okay? Tautomerization, which will of course favor the downward reaction, this reaction I want to draw here. But what will happen here? When you have a terminal, this thing, OH, that is tautomerizing, a terminal enol. What will happen? When it tautomerizes to an aldehyde. It changes to an aldehyde. So an aldehyde, this is a ketone, okay? Propanone, butanone is a ketone. These are ketones, okay? Or alkanal. This one is an aldehyde or this is ketone or alkanone. Alkanone. This one is alkanal. Exactly. So how will it tautomerize? The same procedure. This guy will come and form bond here. So this one will cleave, the bond on this one will cleave, and you will form. Then for that reason, this bond also will cleave to this guy. Then this guy will be protonated. So we have CH, CH, and H like this. Then the C here will take a hydrogen, then bonded to this and double bond this and H. So what do you see here formed? It forms butanal. Is it clear? Remember, this is a terminal functional group. CHO is a terminal functional group. So that's the anti-Markovnikov product, and it happens with hydroboration in the presence of what? A peroxide. There must be a peroxide. I told you the anti-Markovnikov product is also called the Karasch effect, named after the guy that worked on it. Now, the next one is hydrohalogenation. Let's talk about the hydrohalogenation. Number 4, hydrohalogenation. Now, what happens with hydrohalogenation? Simply remember first that what is hydrohalogenation? Addition of what? Hydrogen halide. Addition of hydrogen halide. Okay? We commonly call HX, with the X being the halide. Now remember that there must be an addition in excess. Okay? When you add in excess, then it follows Markovnikov product. Also follows Markovnikov product. Now, why do we always have to mention if it follows Markovnikov product? The reason is because there's when you do the additional reaction of this thing, when you do the additional reaction of this one, for example, the sites that those guys will bind to, they are specific. You understand? They are specific to where they will bind to. We call it regiospecificity. That is the fact that chlorine, for example, if I want to add HCl, let me add HCl to this guy. Now, you want to add HCl. Now, HCl is to be added in excess. That's the first thing. If it must complete, if the reaction must happen completely. But the first thing you have to know is that, as I said, in excess, but the first thing you have to know is that when it cleaves the first bond, the first guy. Where will chlorine add to? Where will hydrogen add to? Now, being a terminal, this thing is quite hard. But it's not hard. Using Markovnikov product, Markovnikov said that this, where is the heavy group here? Chlorine is the heavy group. Hydrogen is the less heavy group. What will happen? Chlorine will come and add to where there is less hydrogen. Between these two places, that's what we want to decide. So our answer will become C123, C12, C. Now, double bond, C. Now, where will hydrogen? This is our former H. Where will hydrogen add to? Hydrogen will add to the guy that already has hydrogen. Then chlorine will come here. Is it clear? So the first product, the first intermediate product that will be formed is what? Is 2-chlorobutane. Do you understand? Not 1-chlorobutane. So that's why we need to always mention that it is Markovnikov product that will be formed here. Is that clear? Because I said it is regiospecific. The addition of this guy is regiospecific. But of course, because it's in excess on further addition of HCl, and to break the bond, again, you ask me, where does it form? Remember, I said it is regiospecific. It will come and stay here because this guy is the one that has less hydrogen. Now, because some might be thinking the next one should come and form a no. The next Cl will still come on this guy and we will form this. We will form this. 1, 2, 3, C, 1, 2, C. So we'll form Cl here and Cl here again. Is that okay? Then CH3. CH3. So on complete addition reaction of hydrogen halide, the Markovnikov product is always formed. And in this case, what we have Markovnikov product? 2,2-dichlorobutane. 2,2-dichlorobutane. Because the heavy group will go, remember that's Markovnikov rule. The heavy group, which is higher, which is chlorine here, if it's bromine, it will be bromine, will go to the side that has less hydrogen. And the hydrogen will go to the side that has more hydrogen. Do you understand? We'll go to the carbon that has more hydrogen. So, and I've told you, of course, the other product might also be formed, the minor product, but this is the major product. I told you 80 to 85% of that is what is formed. All right. Let's go to the next reaction, which will be, in this case, ozonolysis or oxidation. Okay, I've already covered, so I've covered this and this and this. So the last one is oxidation. Ozonolysis, yes, oxidation. So make sure you listen very well here. We're almost done. Almost done. That's number 5 or something. So ozonolysis now. Ozonolysis. Now there are two ways we carry out oxidation. It's under oxidation, okay? It's under oxidation. There are two ways. We use ozone or we use another product. Now I'd like to start with a large molecule first, okay, before I use a terminal this thing. If I have this, for example, now I like to draw it long, there's a reason. I said I wouldn't draw this before. I just want you guys to always see what is happening. Now this guy, but please, you should get used to the line diagram. I'm going to draw this in line diagram. Let's do that. So I react this with ozone. Now when this reaction occurs, what will happen? If you remember ozonolysis in alkene, very simple, it's the same way. Ozonolysis, the ozone cleaves both sigma and the pi bond. Okay? It cleaves both the sigma and the pi bond. So it means to cleave everything, right? So simply come and break it here in the middle. Break the bond in the middle. You know what you now do? You now add O's like this. Add O to all the sides, to the ends. Okay? So what will happen is that by the time this occurs, in the presence of water, of course, what will happen is that the water will protonate it immediately, and then what you will form is two products here. Two products here. What are two products you like you will form here? You will form, just come and write it back. Write what you have on this side, write what you have on this side. What you have on this side will be this, then C, double bond O, then OH. Now this first O is the one that forms this. This second O will be protonated, and then you form this. So with this, what do we form? We form what? A carboxylic acid. A carboxylic acid. In this case, which carboxylic acid did we form here? This will give us 1, 2, 3. That is propanoic acid. Okay? This is the first product. Then plus, what will be the second product? The other side. So write it the same way, like that. The same way. Okay? And, sorry. This is the second carbon. So it will be double bond O, then single bond O, then also protonated. So what would this be? This is what? Plus what? Ethanoic acid. Ethanoic acid. So the product is like this. Very simple. Very simple. Simply cleave it in the middle. So it means that if I have what looks like this, simply cleave, my products will become what? Plus O3 ozone. My products will become what? This, with a 1, 2, there's a carbon here, then this carbon, double bond O and OH. Then here too, we'll have, just draw your molecule. I'm trying to show you if you wanted to draw in skeleton. Draw your molecule, then double bond O and OH. Exactly 1, 2 carbon, 1, 2 carbon. 1, 2, 3, 4, 5 carbon. 1, 2, 3, 4, 5 carbons. Exactly. Now, what if it was a terminal carbon? If it was a terminal carbon, then the product changes. The product changes just a little bit. I'm coming, give me 1 minute. The product changes. So, if it was a terminal carbon, what will happen? If this was terminal, for example, we have something like this. Let's use our butane that we've been using. Now, if you react this guy with ozone, now what will happen? Keep in mind that, of course, it doesn't form directly. There is an unstable intermediate which is called ozonide that is always formed. I've told you this in alkene. Ozonide is formed as an intermediate. So by the time you react this, you break this out, break this down. What will happen is that now this guy breaks. Watch, this guy breaks the same way, and you have this like this, right? So you're going to form 1, 2, 3 double bond O, OH. Then plus, now, it's only one carbon that we have here. That should be double bonded to this O and single bonded to OH. Then, of course, then there's hydrogen here. Now, you see this guy, this is how we should draw it. Now, you see this guy is formic acid, okay? But what happens is that this formic acid is unstable. It immediately reverts to CO2. So if you are told what's the final product of the ozonolysis of an alkyne, of a terminal alkyne, is going to be this CO2. Is it clear? So, but of course, it forms formic acid. Take note of that. Then that reverts or forms CO2 back. Is that clear? But what if this did not, this oxidation did not happen with ozone? What if it happened with permanganate? So let's talk about permanganate oxidation. That is oxidation using a strong oxidizing agent called KMNO4. So if it were that guy, let's use an internal alkyne first. Now, you react this guy with KMNO4. Now, the thing is this, that there are two conditions. There's the neutral condition, such as we find in water, in just water. If this reaction happens in water, If this reaction happens in water, what will come? Please come. If this reaction happens in water, this is like the last one. If this reaction happens in water, how are you going to? This reaction happens in water. Is a neutral this thing. What will happen is this, that this guy will cause these guys to form a polyhydric alcohol. It forms a polyhydric alcohol. And what is the polyhydric alcohol? Make sure you see my video on alcohol too. The polyhydric alcohol is like this, that will be formed. It's just it will add OH. So every time it cleaves this bond. Yeah, by the way, only the pi's cleave for this one. Only the pi bonds. Only the pi bonds cleave. Under this neutral condition. Under the neutral condition, only the pi bonds cleave, not the sigma. So you still have this. Now, but what will happen is that this guy will have OH, this guy will have OH, this guy will have OH, this guy will have OH. And this is very unstable. This is going to be very unstable. Now, what happens is that this guy quickly turns to diketone. A diketone. Now, what's the diketone that will be formed? The bonds will break. Some of these OH will be absorbed into solution, and then we have C. Since the bond is already weak, this bond will break, and then you have C double bond O, like this, and C. Okay, you can put double bond O. C double bond O, then CH3. Okay, I like to just put it up. CH3. No, I like to put them in the anti-configuration. Okay. Now, why did I put them in anti-configuration? It's just simple. You know that oxygen is very rich in electrons. You can't put them together, so it has to go in the so there will be steric hindrance or steric interactions. So because of that, I put them in this conformation. But this is a diketone. So this is what happens if you have a neutral, and if you oxidize with permanganate in a neutral medium. What happens in a hot basic medium? So permanganate oxidation in hot basic medium. What? Tell your mom I'm coming. Permanganate oxidation. No, you're disturbing me. Permanganate oxidation here in hot basic medium. So the same guy, okay, the same guy is going to now react with permanganate, but this time in a hot, so KMnO4. So usually we just put this to represent that this is the active portion of this KMnO4 that is reacting. Is that clear? But now it is hot. It's in a hot, means heat is applied, and basic, okay? It's in a hot basic medium. Now what happens is that because of the very strong conditions, it will be able to cleave both. This one cleaves both pi's and sigma. It's able to cleave both the pi's and sigma bond. So when you oxidize, you have this. But because of it is a basic condition and it's so strong, what you will form is not you will not form ketone directly, like we formed here. You will not form ketone directly. Where is it again? You will not form a ketone. What you will form is actually like ozonolysis there. What you will form is deprotonated base, deprotonated conjugate, no, sorry, it was here that we're forming carboxylic acid, sorry, not ozone. I was saying ozone. The acid, okay, the deprotonated conjugate acid is what you form. Conjugate base, sorry, conjugate base, that's what you form. Okay, how is that going to look like? For this side, it will look like this: CH3CO minus. Okay, structurally that is basically C123, C double bond O and O minus. Okay, and for the other guy, the same thing. In fact, they are the same because they are symmetric. So the molecule we are using is symmetrical. So that's the case for this guy. You form the base, then if you now want to form the acid back, you have to react this guy with an acid, okay, depending on an acid or water, for example, protic solvent, put in the protic solvent, then this guy will now be acidified again, and then you have CH3COH. Is that clear? So that will be it for, no, there's still tests for hydrogen, but we'll do tests for alkynes now. Let me attend to this guy. Come. So, what will now be the test for alkene? Test for alkynes, sorry. Now, just like we have tests for alkene, is just the decolorization of bromine water, right? But with alkynes, okay? Alkynes they decolorize bromine water faster. They decolorize, it's not only bromine water, right? Bromine water and permanganate solution faster than alkene. Who can tell me why? It is because of their labile, right? Their labile. Okay? That's for terminal alkyne. Even internal alkynes also, they are not labile. Internal alkyne are not labile, they are not acidic, that's the mean. But I'm saying that this property also helps them to react faster. Okay? So that tells you that terminal alkynes are less stable than internal alkyne. Is that clear now? So that's what I wanted to point out. But whether it is internal or terminal, they will still decolorize chlorine water faster than alkene. Faster than their corresponding alkene. But how do you now differentiate terminal alkenes? Number one is reaction with ammoniacal copper nitrate. Copper 1 nitrate actually. So when you react that with chlorine, it will decolorize it. I can't remember how they call it now, but it changes to red. I think I remember. It changes to red, okay? That red is when it forms, that red color comes when the alkyne has formed alkinite, copper alkinite in this case. So a copper alkinite. Or we call it copper acetylite, okay? Copper acetylite. And what's the alkinite here? RC triple bond C. Remember? I mean, this C has, okay, C is here. Then there is a negative charge from the two, this in our copper. Okay, so this is copper acetylite. Then the same thing occurs with silver nitrate. Silver nitrate changes to white. Its own color is to white. This one is to red. So the same thing, it forms silver acetylite. Is that okay now? Silver acetylite. So that is the test for, just the color changes what you remember, okay? So do want to subscribe to the channel and click the bell notification to get notified whenever I will drop a new video. God bless you.